Yes, yeah, hi everyone. My name is Dongfu, and as Frank just talked, I'm a first year PhD student led by Professor Chen. And in this presentation, I'm going to talk about my recent publication called TIGERScore, basically towards building explainable metric for all text generation tasks. And this author, it's the following are the authors. So the outline is that I first introduced our paper's motivation in the introduction, including the current matrix issues and what are we aiming for, what is the good universal matrix that we are aiming for. And in the second, after that, we introduced the design of our TIGERScore, how design model architecture or input-output format of our TIGERScore to make it better uniform universal matrix. And in the third part, I will introduce MetricInstruct, which is a dataset we have curated carefully to turn the TIGERScore, actually llama models to a TIGERScore. After that, I'll talk about the experiments and community using how do you use the TIGERScore from Hugging Face, etc., and some conclusions, takeaways. Okay, so first one, what is TIGERScore aiming for? So the first motivation is that the basic motivation is that we want to know, okay, how well can we do to use large language models to evaluate large language models? So currently, GPT-4 has been proven to be a very strong judge, or evaluator for various tasks. You can see GPT-4 as a judge for many benchmarkings, upper level, other benchmarking. Upper level might be the most famous one. And but however, on the other hand, open source large language models is lagging behind in the evaluation ability. You don't see anyone actually using a very poor or very small large language models to evaluate the ability of another RMs, right? So basically, the evaluation ability needs more powerful ability of the RM itself than GPT-4. And another motivation is that existing matrix these old matrix, bird score, etc., they're not suitable for evaluating large language models. So yeah, that's why we introduced TIGERScore is a universal matrix that we designed to evaluate all large language model outputs for basically all tasks. The current issue is that the decision matrix has mainly three issues. The first one is dependency on the references. So like automatic matrix, gold, blue, comet, or recent matrix and explainable matrix in InstructScore, they all dependent on the reference to output a score so that you can compute the correlation to evaluate that so that you can evaluate the quality of the output or something. And the second issue is that limited to the specific domains. That means basically, if you want to evaluate a new task, you have to develop a brand new model for that task only. For example, Comet is only for translation. Brute might be only good for translation and data text or etc. And the third issue is that the current matrix, they also lack of attribution. So bar score, bird score, GPT score, etc. They are only output one number at a time. So no explanation, no natural language explanation. So that's why that's another direction we want to aiming for. So what is a good universal metric? So the first one is that, as we said before, it should be reference free because you can definitely use a reference-based metric to evaluate overall model's performance. I mean, on some benchmark, but in practical scenarios, if you want to evaluate LLMs in practical scenarios, use real world scenarios, it's very hard for you to find a reference for that input, right? So we basically want to develop a reference-free matrix, and we want this matrix to output some evil results. The second one is multiple tasks. So except for you want to use different metric for different tasks, we want to use one metric for basically every task. That's basically what our large language model does, right? Before the GPT-3, ChatGPT, basically you need to specifically specialize language models such as for summarization or for translation. But currently, the large language models, basically they can tackle all of the generation tasks. That's what we want for the matrix too. So we want to do some summarization, translation, etc. for these tasks, and we want to evaluate these tasks in a single matrix that is TIGERScore. And the third property we think is very important, that is explainability. except for so what is the evil result should be? We think that it's first of all it should have a overall rating, right? Overall ranking, overall rating. So this rating is basically the score that per score, they output. And another thing that natural language explanations is very important for you to understand better how these large language models can be used to evaluate other outputs or not. These are very important explanation properties. So the TIGERScore design principles basically follows current issues. First, follow the 3 current issues, and we also add some self-custom designs like multi-aspect evaluation, pattern scoring system, and structured analysis output. We'll introduce one by one in the following slides. So the first one is reference free. So this is actually the input-output figure of TIGERScore. The TIGERScore actually only takes the instruction, input context, and the output to be evaluated as a whole, as an input to feed that into the TIGERScore. So these are no references in your design. So basically, it's a reference-free matrix. Yeah, it's also driven by instructions. That means basically every instruction represents a different task. For example, for the summarization task, this instruction might be, okay, let's summarize this the following paragraphs or summarize the following articles. The data type might be, okay, please change the following structured data into a natural language representation, etc. Yeah, other instruction following tasks with many different instructions. This driven by instruction is actually has a complete job of multiple tasks learning. Yeah, another property is self-determinable. So we design the output of the TIGERScore to be error analysis and explanations. So as you can see, basically we output a series of errors, right? These errors contain the location, aspect, explanations, and penalty scores that we use to evaluate these errors, and we compute the final score as the overall rating of this output. So this contains the natural language explanation as well as the overall rating as a score, which you can actually use to qualitatively to evaluate the output. Yeah, another thing is the multiple aspect evaluation. As you can see, there's actually multiple aspects designed for different tasks. For example, the first one might be relevance because the output might be irrelevant to the instruction or irrelevant to the input or contain some factual errors. And another aspect might be, okay, fluence. This output might contain some grammar errors. Yeah, actually, we have defined very many aspects for different tasks. We have included summarization, translation, data types, long-form query, mass query, and instruction following all 6 tasks. And we have defined basically 3 or 4 aspects for each task. And this is an example of instruction following evaluation aspects. For example, for instruction following, we want to evaluate the comprehension, accuracy, informativeness, and coherence. Basically, the definition is followed by, as you can see in the table. Yeah, the another design of the TIGERScore, which I think is very innovative and proposed by Professor Jiang actually, is the penalty scoring system. Instead of simply assigning a positive score to tell, okay, this output is how good this output is. We instead define some penalty score for each error ranges from -5 to -0.5. Basically, we care for the error. We care more about the errors instead of how good this output is. And finally, we compute the final score by summing these penalty scores, as you can see in the right tab. Yep. The structured analysis output is another thing. So each error is actually consistent of a structured output analysis. It contains location aspect, explanation, final score, and we compute the overall final score by summing up all the penalties. Yeah, the next section is actually MetricInstruct. This is a dataset we have curated to turn the TIGERScore. So how do we curate this dataset? How this curation pipeline is constructed? So yeah, where does the training data come from? Basically, the overall idea is that we have this predefined aspect, and we have calculated some inputs from different tasks And after that, we feed this input to the overall many different systems for different tasks, and we we sampling the outputs of these inputs. After that, we define a prompt template. We simply query GPT-4 to collect and filter the analysis. After that, we feed the predefined aspects, inputs, outputs, and the collected error analysis as the output to fine-tune the llama finally becomes a TIGERScore. This is basically the structure, how the pipeline is conducted. So MetricInstruct actually has some properties. So the first one is dataset diversity. Basically, it has, we have created basically 5 to 6 datasets for each task. In total, we have 23 distinct datasets across 6 general NLP tasks. And we also cover a broad category of errors, more than 50 system outputs are collected. That means we have more than 50 systems for in total for these inputs. So while different systems they might embody some kind of different abilities, right? They might make some errors of different types. So that's why we think that error coverage might be very diverse, or very diverse. Another property of MetricInstruct is the quality assurance. We basically use various heuristics to filter out the bad quality data output by GPT-4. Some heuristics might include, the error location mismatch. Sometimes the GPT-4 can output some errors indicating the location is actually not in the input, it's actually somewhere else. So it's an unreasonable analysis. We drop this data, and it also might contain some illogical severity labels, excessive long outputs, or bad explanation, like simply output a based on the reference, it should be blah 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 instead of blah blah blah. It contains actually no useful information, so we simply drop these kind of explanations. Another property might be a two-channel curation. Basically, we have 2 channels. First one is the real-world channel. And second one is the syntactic channel. The main difference between these channels is that the system outputs are generated from different places. The real-world channel, for the real-world channel, the system outputs is generated from the more than 50 models that we have that we can find on the Hugging Face datasets. They are all open source. For the synthetic channel, the system outputs that might contain errors is actually synthesized by GPT directly. This actually ensures that the syntactic channel can generate more incorrect outputs that can contain broader categories of error types, so that we want the outputs to contain as many error types as we want, so that it can be very diverse. Very diverse in the data sets. After these 2 channels and filtering, etc., we actually get a 32K data after the filtering. So the prompt template, as you can see in the right picture, is that basically for real-world models, we feed the instruction, input context, references, and output to the GPT-4 for the query. But for the syntactic one, we didn't feed the output to that. Instead, we asked the GPT-4 to synthesize the incorrect output. That's why the syntactic channel only takes the instruction, input context, reference, and not the output as the input. So another design of the MetricInstruct is that free-form XPath. So another 10K data is sampled from Upgable 52K. We encourage the reason why we collected these free-form aspects is that we want to encourage various free-form aspects. As you might remember, we have defined 3 to 4 aspects for different tasks, right? So, but these tasks, their definitions and names are actually fixed, and we don't want our model to overfit to these predefined aspects. So we want GPT-4 to generate some out of distribution, the aspect that we have we didn't cover in our predefined definition, so that it can better generalize to the unseen error types or unseen tasks. So for the MetricInstruct, the overall data distribution, we also do the overall data distribution analysis. The contact length basically being the about 1,000, yeah, and we also count the k-arrow instance balancing, as you can see in the right top figure. And so that basically means that each instance, how many arrows each instance contains. The k-arrow instance is actually very balanced. For example, there are about 1,000 examples that don't contain errors. So we want the TIGERScore to learn, okay, which types of outputs is perfect, which type of outputs do not contain errors. And there are also some pretty 1,000 or 2,000 outputs that contain 3, 4, 5 errors. We want the TIGERScore to know, okay, how many errors, different severity of error, different number of the errors. Yeah, etc. And we also balance the severity of the error. So we basically count this in by the penalty score of the GPT-4 outputs. Yeah. Yeah, for the training setting, basically we use the Llama 2 7B and Llama 2 13B, 2 backbones and 2 TIGERScore versions. And you what? Postpone? Okay. Okay. The context length is being 1,000, 1,024, and batch size being 128, etc. Basically, these are training setting. I don't want to basically simply state them again. Yeah, you can see now. Yeah, another thing I need to mention is that we use VLM to accelerate the inference during the testing. VLM is very good at accelerating the Llama inference, so that's very useful. The testing data set, basically we have 5 held in data set and 2 held out data set. Basically the summarization and translation, they are held in data sets, and for the instruction following and the storage and data set, they are actually held out data set that we have that TIGERScore had never seen during the training. The correlation metric we use is actually Pearson, Spearman, control, and we also collected human rating either from the official human rating of the dataset or GPT-4 averaged scores. This is the result actually. So basically some conclusions, the overall TIGERScore. This is a table of the quintile correlation. I didn't put the Spearman and Pearson results here, so we can simply look at the quintile. The conclusion is that overall best across all the metrics. Yeah, as you can see, basically the overall this TIGERScore actually reached some kind of 33.773 overall correlations. Yeah, it's very great performance, and also the best of all tasks compared to other reference-free metrics. It's also best of the 5 out of 7 compared to the reference-based metrics. So the 2 tasks that our TIGERScore didn't beat is actually the summarization and translation. As you can see, the summarization, the uni-eval summarization has achieved the best correlation, and for the translation is Comey 22. We simply think that okay, they are reference-based, right? So they might have advantages over the reference, but we don't have. So that's actually acceptable, we think. The human evaluation is basically we sample 50 samples from each type data set, and we evaluate whether the explanation has errors, whether there are overlooked errors, whether the revised suggestion is useful or not, rather an overall rating. Basically, these ratings are higher is better. And yeah, these are the percentage and that are rated as positive ratings, basically 70%. Yeah, this is very I would think is very optimistic results. Yeah. We also conduct some evaluation study. Okay, we want to see whether the two-channel mixing actually works, and this is the results. The green bar is actually the result of the mixing training of the synthetic channel and real-world channel data. So as you can see, the improvement is very significant, and especially for the long-form QA tasks. And another evaluation study is whether the multitask learning benefit. Basically, we conducted evaluation studies. We trained six separate models that are trained only for the summarization or only for the translation, etc. So the results showed okay, the multitask learning can really benefit, but not for the math QA. It's kind of a little weird. Math QA is pretty hard to evaluate, but because this model needs to have some very strong reasoning ability, so that's for we think that's acceptable. Also, a future direction to improve the math QA performance. Yeah, the community using basically we have very easy to use APIs in our GitHub repo. Basically, you can use TIGERScore, just 3 lines of code. As you can see in the right, basically, we also support the inference speed actually with VRM is 5 or 4 instances per second, which we think as a metric is kind of acceptable. And there is also an example of the structure analysis output in the JSON format. Yeah, Convey TIGERScore has curated some downloads on the Hugging Face. So the conclusion and the takeaways is that we released TIGERScore and we released a new pipeline to curate the MetricInstruct, and we achieve the overall best performance compared to other metrics. And the limitation is that actually we still generate hallucinated errors or false explanations sometimes, as we can see here. So there are still sometimes the explanation has contained some errors, and there's still sometimes revised session or not useful or overlooked errors in the evaluation results. So that's kind of future improvement points. Yeah, and it's also not good at evaluating resilient tasks at the math QA. We think it's actually pretty hard to evaluate math QA. Yeah, potential use cases basically you can first one is very naive one. You can you apply the TIGERScore to the large scale reward evaluations, and it's explainable. So this is a very important feature. And second one might be the serve as the fine-grained reward models to enhance our abilities to intern. This might be in future work. Yeah, we are still thinking about it, but there is a paper called fine-grained reward modeling. I don't remember exact names. Basically, that can use the fine-grained rewards to improve the abilities of RMs iteratively. I don't know, but TIGERScore might be very suitable for these kind of tasks. Yeah, that's all for my presentation.